Hi everyone, this is Zhenyu. Welcome to my talk on our paper Learning Acoustic Scattering Fields for Dynamic Interactive Sound Propagation. Sound propagation is the phenomenon where surface vibrations of objects produce pressure perturbations that are received by a transducer, for example, human ear or microphone. There are different types of interactions in sound propagation, like sound occlusion, reflection, and diffraction. These interactions significantly modifies the sound signal. I'll play two audio clips. The first is dry sound or clean sound from the source. The second is a reverberant version after propagation, heard by the listener.
Buck did not read the newspapers, or he would have known that trouble was brewing. Buck did not read the newspapers, or he would have known that trouble was brewing.
The propagation behavior of sound in a room can be characterized by the so-called rolling pulse response. Conventionally, we decompose the RIR by the order of reflections. There are direct sound early reflections and late reverberations. The final rolling pulse response is constructed from many individual sound propagation paths that each have associated information about the time of arrival, direction, and intensity. The straightforward way to simulate sound propagation is exactly by generating a lot of rays from either the source of the listener, and whenever they hit an object surface, the energy carried by the path will be attenuated, and when they arrive at the listener, it creates a delayed version of the original sound. This is called ray tracing and is most commonly used in a geometric acoustic context. However, geometric sound propagation relies on the assumption that sound travels as rays, which hold for high-frequency sounds but do not work well for low-frequency sound. The wave characteristics of sound can be modeled by the acoustic wave equation, which creates wave effects like diffraction. While there are numeric wave solvers available, they require a lot of computation time and are not suitable for real-time applications. Recently, Fan et al. Creates synthetic 3D objects by extruding 2D sketches and computes the 2D loudness field slice around the pillar-like object. Then they use a full-resolution residual network to predict the scattered field from the 2D sketch image input. Inspired by this work, we decide to propose our solution to a more general 3D scenario. We predict the localized wave propagation results using deep learning and combine them with existing geometric sound propagation engines for VR, AR, or gaming applications. Our contributions include learning-based 3D acoustic scattering fields and an interactive wave geometric sound propagation engine. Our engine also generates plausible sound rendering for dynamic scenes. Finally, we performed a perceptual evaluation. As for dataset generation, we processed 300,000 3D meshes from the ABC dataset. The original meshes are used by the FastBEM software to compute the ground truth acoustic scattering fields. We use point clouds as our 3D object descriptor, also as the network input. High-dimensional acoustic scattering fields are converted to compact third-order spherical harmonics coefficients, also as our learning target. We run the wave simulations on a multi-core Windows 10 workstation for 10 days to compute the acoustic scattering fields for all 300,000 objects at 4 different frequencies. When simulation is done, we train 4 network models for all different frequencies. Each network is trained on our modern GPU for 10 hours. We aim to present a proof of concept implementation for our idea, and we borrowed PointNet architecture to extract global features from the input point clouds. Then we used 3 multi-layer perception layers to regress the spherical harmonics coefficients, which represent the acoustic scattering field. While it is possible to find better structures for a problem, we do not extensively experiment on that aspect. As for evaluation, the predicted spherical harmonic coefficients are expanded for all spatial directions. The ground truth spherical harmonics computed from FastBEM solver are also expanded in the same manner. The difference between the two results are measured by a commonly used metric for sound field reproduction called normalized reproduction error. We show visualizations of our results. On the right side of each object, the first row shows the ground truth or target scattering field by frequency, and the second row shows our prediction results with annotated reproduction error, which you may interpret as percentage error. Note that all test objects were not seen during training. Here we show more results. We are also interested in how well our method can generalize to more difficult scenarios. On first row, we show two separate objects that move towards each other to form a new composite object. On the second row, we show a deforming object. While we do see a rise in the reproduction error for these cases, the results are still promising. These cases are not intentionally created for the training set. Because we are essentially dealing with a regression problem, we would like to know the error distribution in addition to the average error. We observe that most of the test errors are below the average error. Based on the predicted scattering field, we built a hybrid sound propagation engine. Conventional ray tracing algorithms query the ray energy by using the bidirectional reflectance distribution function, called BRDF. Here we replace it by evaluating the acoustic scattering field, which should be compatible with most ray tracers. The hybrid sound propagation scheme has two parts, an offline training part and a runtime part. For the runtime part, the outgoing sound energy can be evaluated from the acoustic scattering field. When a far-field wave intersects a scattering object, nearby objects are also considered for ASF computation. Our ASFs are predicted dynamically. In order to understand the perceptual benefits of our method, we run 4 test benchmark scenes involving multiple dynamic scatterers. The audio-visual renderings are also used in our user evaluation, which shows our method has perceptual differentiation over prior interactive sound rendering methods. For more details, please refer to our paper and project site.